Puedes venga, estás.
Oh, no, always very nice. No,
I think we can start the power use before, right? Before the start. Yes.
Sì, io le Okay. Hear me?
Yeah, I guess
Okay. For me, it's a great pleasure to introduce Dr. Oleksandra Ivanova from the Astronomical Institute of the Slovak Academy of Science. Oleksandra is here in the framework of the Erasmus Plus program with Olena. They came to collaborate with our group in solar system science. She made her PhD in Kiev, in the main astronomical observatory of the National Academy of Science of Ukraine, where she's been working. She did a PhD in 2004 and been working there till 2016 as a researcher, and then moved to the Slovak Academy of Science in 2016, where she is a senior researcher. Oleksandra works in comets. In particular, she's an expert in dust and chemical composition of comets, doing different kinds of observations, imaging, spectroscopy, and polarimetry, which is one of her more important contribution to the field. And I think it's enough. Thank you very much for being here.
Hello, everyone. First of all, I want to thank Dr. Alejandro for invitation in your institute, and I hope our collaboration will be long and very productive. And today I want to talk a little bit about my main subject of my work, it's comets, and a little bit talk about properties, scattering properties, not typical objects, it's distant comets, and I talk.
Okay, Microsoft. Go ahead.
And before my talk, I a little bit present our institute. Originally, I'm from Ukraine, but a long time I worked in Slovak Astronomical Institute of Slovak Academy of Science in Department of Interplanetary Matter. You can see here it's my building of institute placed and located in High Tatars. And we have 3 departments. It's solar department, interplanetary matter, and stellar department. And we have some telescopes, 2 small telescopes, 70 centimeters, located here near the institute, and usually used for photometric and spectroscopy of stellar objects. Here in Lomnitz sheet, you can see it's placed solar telescope, and usually there working our people from solar department. And our department has two telescopes here from another lesson. You can see here, we use usually two telescopes, small telescope, 60 centimeter for photometry of small bodies, and 1.3 meters, it's usually for photometry and Edgeworth spectroscopy of small bodies and stellar objects. Also. And my talk today is about comets, their properties, physical properties, and chemical properties, which we observe. And we talk about a little bit for activity in great range of heliocentric distance. How we know cometary is ice-conductive objects, which usually we have all properties, and understand from physics of comets, from observation, ground-based observation on space missions for comets which come to very close to the sun. Usually it's short periodic comets or long periodic comets which observe heliocentric distance less than 2 AU. Before water ice or water snow lines, and main mechanism of activity of comets at close to the sun is sublimation of water ice. And for most of comets, we see very rich gas emission spectra with dark. And how you know, most of cometary missions, it was only for short periodic comets, and most of information from comets we have only for observation of comets very close to the sun. For me, it's more interesting another objects which presented some very high activity beyond water sublimation line. And for these comets, it's comets with perihelion distance more 4 AU, and sometimes we see very long-lasting activity of their objects, very far from the sun. And for physical mechanism of activity, their objects provided some mechanisms. It's sublimation of more volatile components, CO, CO2, and other. And for example, proposed transition phase between amorphous and crystalline lines in cometary nucleus, and less mechanism proposed by which is annealing of amorphous height in cometary nucleus. But question about mechanism of activity in large heliocentric distance still stay open. And study and analyzing observed distant objects is very important for understanding the condition of formation of small bodies, relation between Kuiper belt objects, active controls, and another comets. We need better understand which usually for us important how and where formation of different objects in protoplanetary disk, and where formation of different objects which we observe. And in 2006, our group started a new program. It's a ground-based observation of distant comets with perihelion of 4 AU beyond the zone of sublimation water ice at 6-meter telescope using some focal reducer scorpio, which this reducer allows to us to use 2 modes. It's a photometric different filters and lucid spectroscopy. And in 2011, it's attached a 6-meter telescope new focal reducer Scorpio 2, and included in this focal reducer new mode, it's polarimetric, and we include some polarimetric in our program of observation. And also we all time observe and make some long-lasting photometric observation of selected distant comets in different middle-sized, small-sized telescope and different parts of line. And main purpose of observation for our project was comets with very different morphology and different level of activity. It's with compact coma or long tail, but its activity is very high before perihelion. Purpose of study included construction some gas emissions or ions in spectra, analysis of the spectral energy distribution of different parts of spectra, modeling some details, analysis of polar maps and understanding its temperatural formation and its chemical composition, how change dust productivity with heliocentric or distant. Really, the particle change properties with heliocentric or not. And of course, it was modeling interpretation of formation of dust tail and ionization from gas with big heliocentric distance. And you can see we used different methods, usually quasi-simultational methods together, including photometry, spectroscopy, and polarimetry. For photometry, we used different filters. For distant objects, usually we use broadband filters because the inspector not presented any gas emissions. And for such objects which presented some gas emission, we use cometary filter. It's a one filter which allows us to isolate some gas components or dust. From photometry, we try to obtain many physical parameters, including dust-to-dust production rates, and look how change dust productions and dust production with heliocentric or distant with evolution for different objects, and compare, for example, distant objects with shorter comets and Jupiter family comets and so on. Also, including we try to do some models and obtain some parameters as radius of cometary nucleus, analyze morphology of cometary nucleus, how it changes with level of activity in heliocentric or distant. Analyze colors, not only near the nucleus, but around the coma and along the tail. Obtain some period observation of cometary nucleus at all. And from spectroscopy, we usually long slit spectroscopy because most of distant comets is very faint. And we try detecting some gas emission ions and also obtain some parameter reading and dust production rates and compare with photometry. And from polarimetry, usually we use linear and circular polarization. Circular polarization most for close to the sun comets, but for distant comets, usually we obtain some parameters of linear polarization, do some maps of linear polarization, how change scattering properties of the dust and from linear nucleus with cometary or distant or with the tail. And of course, by that ground-based observation, together we obtain some limits from our models and use different models and work with different groups to model some scattering purposes of dust in small bodies. Active small bodies, we obtain some parameters of the dust size, orientation, composition, its vacuum density, and so on. We presented some short statistics of our observations in 2006. We can see here it's most of them is 46 object. It's distant comets, but they have a distant morphology. Near 20 object, it's distant comets with perihelion distance more for 2.5 AU before 3.5. Where mechanism of sublimation is concurrent between CO2 or a little bit water ice segregation. And we can see here is we also observe active chemicals and 3 active asteroids too. And we can see here some morphology of selected distant comets. You can see it's here presented very different heliocentric distance of observation of this object. And we can see most of them have a very compact coma with long tails. And if you compare with short periodic comets with active, here practically not detected any jets, only 1 or few jets, small, mostly without any jets and active structures in coma, only compact coma, but very different forms of tails. And another type of distant comets, it's practically not presented any long tails, but asymmetric coma, and all activity presented by included many jets, shells, jets, and so on. And we can see these very interesting objects. We first observe more 15 AU, and each object presented higher activity. A little bit spectral distant comets. We can see here some examples of different objects with different heliocentrical distance, and we can see in spectrum we can see any gas emissions typical for comets. Because comets fall to the sun, but there are many gas emissions in cyan, and all islands and nature. But for distant comets, it's usually any gas emission. And most of the cases, we can see already in the spectra, it increases factors potentially with veiling. But for some few objects, we can see opposite situation. We have increasing or scattered potentially in blue region. From modelling, we obtain that for similar objects, we can see many ice particles in cometary coma. From all our observations, we found only 4 objects which presented some gas emissions in large heliocentric distance. Most of working with comets know this object. It's very specific object. It's comets and chemical, and we can see most of them in spectra presented some ions, CO+, N2+, and 3 comets very rich CO+, N2+ objects, and for most of these comets we detected cyan and T3, 1 objects, and very interesting this object, linear, we detected CO+, N2+, very far from the sun, more 8 EU. And we discuss there about mechanism of ionization with large heliocentric distance. This question is a little bit open now in cometary physics. And a little bit about CO+ and 2+ ion distant comets. This question is very important because the study of this selected object with rich CO+ and 2+ ions in the spectra is very important to understand its temperatural formation of most of objects. And we can see here in comparison some distant comets with another comet, it's long periodic, short periodic comet with CO+ and 2+ ions in spectra, but most of them observed very close to the sun, less than 2 AU. But only some comets presented CO+ and 2+ very far from the sun, and all of distant comets maybe formation very far from the sun in our clouds with temperature less than 30 kelvins. And how you know M2 was detected in comet Churyumov-Gerasimenko from Zeta mission and supported about some different places formation of comets in photophotometric. A little bit talk about dust productivity because most of coma and tails of different comets formed by dust. And here we can see some comparison, and here it's comets from Jupiter family comets, short periodic comets. Here it's long periodic comets in different heliocentric condition, and here presented some active centaurs, a checklist maybe. And we can see that most of different comets have very high dust productivity to comparison with another type of comets and centaurs. For distant comets, it's very interesting because high activity usually before perihelion. After perihelion, its dust productivity very quickly decreases, and to opposite short periodic comets, which usually very active in perihelion and short time after perihelion. And we can see here for one comet, we can see its parameter IFO, it's to correlate with dust productivity level, and sometimes dust productivity different filters is different. Usually it's dependent from different properties of the dust and different wavelengths and scattering in different filters. And usually we see different particles in the coma, which we can see here, and we can see also fragmentation particle with comet-centric distance. And next, it's polarimetric of distant comets. When we start this polarimetric observation of distant comets, in literature presented maybe one result of Schwartz-1. It was aperture polarimetry. Before our observation, we haven't any detailed polarimetry map of distant comets. We can see its polarimetric for distant object. It's very different, and properties of the dust very different in near nucleus area in jets, and changed polarization with heliocentric distance. We can see here, for example, one object is one linear at 6 and 7 AU, and we can see its polarimetry is changed. And for example, it's very interesting. We obtained polarimetric map for very distant objects. Object at more 9 AU, and it's very active and forms galaxy-like form observed more 4 AU of these objects, and practically not changing this time in heliocentric distance. And our photometry and polarimetric observation, we try to obtain some parameters of particles of distant comet and understand it's really different dust in distant comets in comparison with short periodic comets, and we can see different models. It's dust as a set of aggregates, agglomerates particle is very compact, random Gaussian particles, and rolled spheroids. All models working with different objects, but usually Gaussian particles better working with shorter comets and comets which observe it very close to the sun. For different comets, we see here it's Negative polarization, small phase angle, better working Rhodes model. It's very fluffy objects, fluffy particles. And here we can see different examples, interplanetary dust particles and dust particle from Cosima, from Rosetta missions, and Rose of course model, but it's very good working with this ground-based observation. For modeling, we use different materials for understand the chemical composition of particles. We can see here it's usually working with halide dust, amorphous silicates, water ice, CO2 ice, amorphous carbon. For organics, we used usually titanic, toluene, and cosmic organic refractory particles. I want to present some main results for different very interesting objects. First, it's object it's SONEAR. We observe this object at heliocentric orbital POEU. It's small phase angle. For this object, not any gas emission was detected in the spectra. It's very red object, spectral gradients, it's more 20, for comets usually it's from 7 to 15 presence. It's very red, and the same for nucleus, it's very red objects. Dust productivity is high, to comparison with, for example, for Jupiter family comets, it's large heliocentric distant, it's typical, I call it 20 before 100 something like that, but for SONEAR it's more higher. And polarization, we can see here it's color map, it's polarimetric map, and we can see here it's morphology. We analyze the morphology. We apply some digital filter to select some fine structures, and for this object we can see very long tail and a small shell near the nucleus, and we can see from polarization map the polarization change from -3 or -8 in the tail, and we can see the polarization patterns of the dust changes in structure and near the nucleus and along the tail. By that, our observation that we used to do modeling and obtain the coma and tail formation from dust particles of sigma size with compensation with many ice particles and many organics. Of course, the most of particles you can see here, most detailed. For example, for polarization in tails, when we have polarization -8%, we need some organic particles with radius most 3 microns, very porosity particles, and we need many ice particles in the tail. Polarization closer to the nucleus, -5%, the same, very close, it's particles more 3 microns, with porosity near 13%, and many ice particles. Near the nucleus, the polarization is smaller, and we can see here its porosity is a little bit changed, but the size of organic particles is the same, more 3 microns. And also we obtain from polarimetric and photometry for modeling, we need have some fragmentation. Maybe it's fragmentation of break some particles, fluffy particles, or sublimation of dirty ice particles, which are fall on the cometary nucleus. Next interesting objects, it's between distant comets and centaurs. It's Spacewatch. We observed at 5 and we can see this object has the same very galaxy-like form. the coma formation by different jet structures. We can see 4, but after modeling, we search the two jets formed from one active area, the same jets, and we have which forms this cometary coma. Also, for this object, we detect some ions, CO+ in the spectra, and will also color and polarimetric map. And we can see spectral gradient to comparison the ison is lower and more natural, and dust productivity more higher to SONEAR comparison. And this object have very big nucleus. We compensate some coma and try to obtain some signal from nucleus, and diameter 47 kilometers. If you use some this algorithm, and we found that for the properties of that very change near the nucleus, and also we see change some color in along the jets, and after modeling, you can see here, we found we need many ice particles of CO2 components, and particle in along the jets 1 and jet 2 is very different in comparison with J3, J4. We can see here we can see more CO2 flows of particles and water particles, and another part is more Haledas particles with including water ice particles also. And next, our object is B1 Schwartz. It's very decent object. It's very interesting because form observed not changed many years, and coma formed by two active area which plays near the polar, and from two jets, and we can see from the color map. Sorry, yeah, color is changed a little bit redder along the jets, and change it around coma. And polarimetric, we can see here, it's increasing with cometary distance, but we can see some area with different polarimetry only increasing with cometary distance. And we can see here some comparison. It's linear polarization to phase angle for different comets. Presented here, it's short periodic comet and long periodic comets from database base for comets, and it's the same very close phase angles, and we can see that polarimetry of most distant comets is different, it's higher than another comets, and we can see its object the same, very red, with very high activity, very far from the sun, and polarimetry we can see change from -1 with the nucleus and decreasing before 6% in limit of coma. And after our modeling, we can see here we use very fluffy porous particles. We can see that usually it's coma formed by aggregates with monomer radius 0.18 microns. Near the nucleus, coma formed by side particle near 1 millimeters and very high porosity. Of course, without ices, ices particles, it's very difficult to explain the big polarization for these comets. And also we need including some fragmentation of sublimation of particles. And some short summary. After 30 sessions of observation of these periods, we observed many different objects in spectral, photometric, and polarization mode. And only 4 comets presented some emission in the spectra. Some comets very rich to CO and T+, and formation very far from the sun with very low temperatures. And we found that particles in coma and distant comets different to short periodic comets and comets very close to the sun. And in coma or distant comet presented many ice particles which this time fragmented and sublimated the size of particles. And few words about our work now here in this institute. We together working with new observation of active asteroids. It's we have very long observation set from July to January to present December, but we have activity in the same January 2022. We have first observation, polarimetric observation of this object in period of activity. Of course, we have polarimetry of different asteroids, but in non-active phase, but it's first observation of active periods. And question about mechanism of activity of this object on this active asteroid is open. And I present some future our workshop, which will be next year in Slovakia. We organize it together with Oleksandra. It will be in the beginning of September, and including our ground-based observation laboratory and modeling, presentation about different object active small bodies in wide range of heliocentric distance. And thank you for listening.
Well, any questions in the audience?
The last observation of where they can be done in Slovakia, which telescopes you use for that observation of asteroids?
Of asteroids, we use Slovakian observation, but fortunately we use 6-meter telescope before the war, yes, and 2.5 also in North Caucasus. Yeah. No, it's called telescope. It's called the ENS. Now it's unfortunately not.
No,
Before, yes.
More questions?
Very impressive. To observe comets at such distances and detect gas and do polarimetry is not an easy task. I know very well. It's very difficult, and I'm surprised with the results. I have a question regarding you mentioned one of the comets you observed. The abundance of water ice particles increased with the comet distance. I think that was the previous one. When you show the model that the results on dust on the particles at different distance from the comet. This one.
Yeah.
It's so near the nucleus, the abundance of icy particles is smaller. But what is going on? Something is happening with the icy particles or with the dust or organic particles.
For most of these comets, formation in jets, and jet formation from different local areas. And our opinion is maybe we see in coma different particles, different which form a different local area. In this moment, we have seen different component composition and size. And maybe we have very fluffy, which included some ice particles in fast fluffy particles, and we see some fragmented. And we see different, with time, different selections of particles in the format.
So the fragmentation along the
Yeah. It depends. We have, for example, many jets, and in jets, one particles, one size, for example, and it's quickly fragmented in jets, for example, because a little bit velocity different, but it's of course it's a model. It's good for photometric and polarimetric because we have some limits parameter of model. You know, it's need to better understand, because if you use only, for example, polarimetry, we have one sided, but after including some parameter for photometric, some limits, and delete some results. But rarely we see, and water ice also need included in this component. Maybe not sublimated, but included in some materials. Yeah. Yeah.
Please.
Well, very interesting thoughts. So maybe it's very different simple question, but I missed maybe the definition of distant comet. Because I was wondering what is the difference between short period and distant comet. We're looking, and maybe you are thinking what provoke the activity is different between the distant and the short period.
I think it's dependent on mechanism of activity. If we think about for example, if we talk about transition between a motion and physical, and we have observed something from cometary nucleus, and we can see more ice particles. But questions the same: how change the properties of the dust if, for example, distant comet go to closer to the sun? Maybe we see another pictures of composition and cometary. But now we see the really the polarization look very different to short periodic comets or long periodic comets, or was but very close. Really is different, and we need to understand it's and include very porous particles and many ices. But it's maybe, but of course, I am observer, but modelist is included some parameters, and but we can see we need some understand why is polarization very low here in this. And from model we have only it's very close particles and many ice, but it depends with the CO or CO2. Ice particle, water particle, but we can see also understand that fragmentation is not only breaks on matrix, but it's maybe sublimation. Like component from if you have a corner of dust and fluid some ice, and this time it's sublimate and change ice and composition, you know. But really, it's before our observation, we observe this aperture polarimetry. In aperture, we give some only near nucleus area, and when we have some polarization map with LSD, how changes properties of the scattering particles in different parts, in jets, for example, or near the nucleus and the coma. But it's the polar map and polarimetric is very difficult for models. They usually working with phase curve, this polarimetric change with phase angle. But here we can see there's some practical energy here for distant object, but we see a full image of different properties.
So, do you think this difference is because of the original distance or origin distance? Yeah, origin distance.
Now,
Basically, you see the difference between comets formed in the Transneptunian belt or comet that came from the Oort, right?
Right, yeah.
we try with different types, of course, but really we see so some objects very rich CO+, and it's a very big question. It's really formation in one place together all small bodies, or they formation in different with different temperature. I supported today about different places because we really see it's for example, comet Schwartz-1 is now it's Jupiter family comets, but they talk about its Centaur, and it's very active object with many CO in radio wavelengths, in ground vessel transit we see CO+, but it's very different to another comet from Jupiter family comet. It's really migrate from another. And also a very big question for Schwartz-1 because we see it's really CO-rich object, but Peter looked some particles and finding particles which form very close to the sun in my belt or radio. And very big question, how this very another particles with very high temperature is object form very close to the sun. Of course, we will not see any gas CO rich object, but we have many questions. Very
So any other question from the audience? So thank you for your talk. You know, and maybe the differences are not really intended to offend, but why there is such a huge difference between the theoretical model and the observations in one of the last figures?
last
Next.
Here.
Next.
Okay.
One more. Here.
Here. Yeah, here.
Yeah, this one.
Yeah, we present some parts less from our colors, and we can see it's for example, for these objects, we can see it changes colors. Here it's in jets, and here it's a coma. And we really see its properties in the jet another. And the polarization properties was detected different in jets and stable coma. For comets, it's very close to the sun, for example. It's really they have different properties because formation in different parts of the nucleus. And also, it's very hard to interpret all variation from color. And for example, here you can see it's very stable changes of polarimetry. And here you see it's we
near the nucleus very high red color, but very low polarization. And for this distant opposite situation, very high polarization and practically neutral coma. And it's our limits for our model. We try, we have limits, but we need understand. Finally, we have this critical points model. It's very hard. I understand it's only model. We understand it's only model, which I understand, but quasi-simultaneous observation help us to separate and delete some parameter and that result. But we really see that scattering property without changes in element.
Okay, thank you.
Any other question from the local audience? If not, let me check.
No.
Okay. I can't end this seminar. I'm really excited. We found waiting this. What are ocean particles?
It's it's very yeah. For me, as I'm observer, and we have 4 groups in one working with really scattering over, so that's regulates known. It's important part because very big working with regulates and without atmospheric objects.
Atmospheric.
But of course, we understand that aggregates with spheroids is not very close to realistic particles, but really agglomerates model is very good working with short periodic comets that we have very close to the sun and particles we have very compact. But they have a problem with particular changes in the size particle in this model. And this model working only for small particle, and very bad with really.
Where are the forecasting? They shape distributed under an ocean distribution function, or where are the forecasting?
I'm not specific, unfortunately.
All right. Thank you everyone for attending the talk and the question. Now we're not. Oh, by the way, this is a PhD student who wants to find out his name. Please do it now. This is a copy. It's a copy, right? We should go and we now which is open. This is a copy of it.
Nada, el desarrollo de